Welcome to Daily Papers, the podcast where we break down the latest and most interesting research into bite-sized pieces.
Today we're digging into a paper that sounds like a video gamer's dream. Imagine an AI that doesn't just learn to play a game, but learns the very rules of the game so well that it can write its own mini version of it.
Exactly. The paper is called Mind Studio, Executable World Models with Lookahead Evaluation for Partially Observable Games. And it's all about teaching an AI to understand the why behind a game, not just the what.
Let's start with that big term, world model. It sounds very sci-fi, but the concept is actually something we use all the time.
Right. A world model is just an internal representation of how the world works. You have one. If I hold a pen in the air and let go, you know it's going to fall. You don't have to see it happen. Your brain has a world model of gravity.
And for an AI, having a good world model is a superpower. If an AI playing a video game has a world model, it can simulate what might happen next. It can ask itself, if I press the jump button now, will I get the coin or will I land on the spikes? It lets the AI plan ahead.
But here's the problem this paper tackles. A lot of AIs that try to do this just learn to predict what the next screen of pixels will look like. It's like guessing the next frame in a movie. It's a prediction, but it doesn't show a deep understanding of the rules.
And that's the key difference. The researchers behind Mind Studio wanted to create what they call an executable world model. The AI doesn't just predict the next image, it writes an actual runnable computer program that simulates the game's logic.
So it's not just guessing what happens when Mario jumps. It's writing the code that says, when the jump button is pressed, increase Mario's vertical velocity by 10, then apply a gravity value of -1 each frame. It's learning the physics engine of the game.
So how does it do it? How do you get an AI to become a programmer just by watching a game? The process is really clever. First, the AI watches gameplay footage of classic Atari games like Montezuma's Revenge, Alien, and Skiing.
But it doesn't watch everything. If it just watched hours of a character walking across an empty screen, it wouldn't learn much.
That's right. It uses a method to select the most informative moments. The technical term is entropy-based selection, but you can think of it as an interest filter. It pays attention when something important happens. A player collects a key, an enemy appears, a life is lost, or the character bumps into a wall.
It's focusing on the moments where the rules of the game are revealed.
Precisely. It then takes these interesting clips and compresses them into a simple summary of what happened. For example, player was at position X, player pressed right, player is now at position Y, and the score is 10 points higher.
And this summary is then handed over to the brains of the operation, a large language model, or LLM. This is the same kind of tech that powers things like ChatGPT.
Exactly. The LLM gets the summary of important events plus a little skill file that gives it basic hints like what the objects in the game are called and what buttons the player can press. And its job is to act like a programmer and write a Python program that could produce those outcomes.
So it's essentially a logic puzzle for the AI. It's saying, here are the inputs and here are the outputs. Now write the code that connects them.
And the results are pretty stunning. To test their new AI-generated game simulators, they gave them to another AI called a planner. The planner's job is to actually play the game.
And because it has this executable world model, it can look ahead. Before committing to a move in the real game, it can run a quick simulation in its own minigame. Let's see. If I jump left, the model says I'll fall. If I jump right, the model says I'll get the sword. Okay, I'll go right.
And it worked incredibly well. For the game Assault, Mind Studio's model was able to predict the outcome of an action with about 95% accuracy. The models that just tried to guess the next state or right less than 1% of the time. That is a massive leap in performance.
And for Montezuma's Revenge, which is a notoriously difficult game with lots of puzzles and hidden rules, the planner AI using the Mind Studio model was able to consistently complete 5 of the 8 major goals in the first level, like getting the key and opening the door.
What's really cool is how it handles partially observable states. That's a fancy way of saying you can't see everything on the screen. There might be a hidden timer or an enemy that always spawns after you pick up a certain item.
Because Mind Studio is trying to write the underlying rules, it can infer these hidden mechanics from the gameplay it watches. It learns not just what moves, but what causes it to move.
So, why does this matter? It's fun to have an AI that can master Atari games, but what's the bigger picture?
This is a step towards creating AIs that can build a deeper, more causal understanding of the world around them. Instead of just recognizing patterns, they can start to understand the mechanisms that create those patterns.
You can imagine this technology being applied elsewhere. A robot in a warehouse could watch humans and not just mimic their movements, but infer the rules of the warehouse, like heavy boxes go on the bottom shelf or fragile items are handled in a certain way. It's about building a more robust and adaptable intelligence.
So, this paper isn't just about building an AI that's a great gamer. It's about building an AI that's a great student of systems, one that can watch, understand, and then recreate the rules of any environment it's in.
Just from watching a game, the AI is effectively becoming a game developer, and that's a pretty incredible leap.